So I think that's the Alon's technique of forcing us to take breaks. It's like, oh, projector's gone. Okay, so we were talking about channel variation with time. Okay, so we figure out that the Doppler spread is an important number. The Doppler spread in turn depends on the carrier frequency, depends on the speed of the vehicle, and also depends on the angular spread. Now, I want to return to this channel variation question, and let's look at our expression again. The nth channel tab depends on the gain of the paths as well as the phases. Okay? So when I talk about Doppler spread, I was referring to the variation of the phases. What about the variations of the amplitudes? Why didn't I worry about that? Large scale. That's right. So that's why that's one thing very important to think about in wireless communication, is that, as you can see, even in a short 1 hour, we've introduced quite a lot of different physical parameters and so forth. The good thing about wireless, and the important thing about wireless, is that a lot of the quantities are very different in orders of magnitude. So the change in amplitude is a very large-scale effect. So it's taking place at the order of minutes. So that's why when we talk about variation of this, we were talking about these phases are rotating very fast, like at 100 hertz or 50 hertz. But this is very slow. So we just sort of ignore that and assume it's more or less constant in the time scale of interest, and just think about this variation. On the longer scale, of course, these gains also changes. Okay? Now, there's actually a third, so this is a trick question. There's actually a third source of variation of this channel tab, which is not explicitly written here, but it is there. Remember, what is this sum over? This sum is over all the paths that arrive in. So I always have quizzes every now and then, just to make sure people are on track. Sorry? It's the sum of all the paths in the bin. So that means that there's another form of variation. There's another source of variation in this gain, a particular nth gain. Well, paths will change the delay, right? So as the delay changes, it can potentially move from one tab to another tab, from one bin to another bin. Why didn't I take that into consideration? Maybe that's also important. Maybe I should not ignore that. Okay? How much time does it take for that to happen? So you have a delay bin of size 1 over W. A path may have arrived at this time with a certain delay, tau of t. As I move around, this tau will change with time, and maybe this path will drift to another tab. And therefore, its contribution, now it moves from contributing to this tab to the next tab. That is another form of variation of the channel. But I ignore that. Why? How long does it, what's the time scale at which this will happen? This will happen when tau t changes by order of not coherence time, be careful. Order of, in terms of this picture, 1 over W, right? If it changes by 1 over W, then it changes from one tab to another tab. How about the phase rotation effect? How much does the delay have to change by for a phase to rotate significantly? 1 over Fc, right? So this is 1 over W, and that is 1 over Fc. So in a typical communication system, what's the relationship between W and Fc? W is typically a much smaller number compared to the carrier frequency. IS-95, 900 megahertz carrier frequency, bandwidth 1.25 megahertz. So 2 orders of magnitude larger. Actually, 3 orders of magnitude larger. Okay? So this number is much bigger than this number in a typical wireless communication system. And therefore, it will take much, much longer time, 3 orders of magnitude longer time for this to happen than for the phase to rotate. That's why we ignored it. Now, so it's important to understand why we ignored it, because it could be that in some communication systems, this relationship does not hold. Can anyone give an example of a communication system that this relationship does not hold? Ultra-wideband, right? In an ultra-wideband system, we're operating at 3.1 gigahertz to 10.6 gigahertz. So this is the bandwidth. The carrier frequency, if there is such a thing called carrier frequency, is smack in the middle. And so the bandwidth and the carrier frequency is the same order of magnitude. So this assumption does not hold anymore. And therefore, we have to take that into consideration if we want to think about variation of the channel. Okay? So that's why it's important to understand the assumptions of the phenomenon. Okay. So, all right. So now we're in a position to give a categorization of the different types of channel that we will see. It's important to characterize it because it turns out that you will have to use different communication schemes for different types of channel. Okay? Now, let me focus on flat fading. We've already defined that. That is when the bandwidth W is much less than the coherence bandwidth. Frequency selective fading is the other way around. So I could do an analogous definition of fast fading versus slow fading. So fast fading versus slow fading refers to a temporal variation of the channel. Temporal variation of the channel. And to define that, I needed to define it with respect to some natural time scale. Okay? So here, the natural time scale I would define it is I define a fast fading channel as one in which the coherence time of the channel, is much less than the latency requirement of my application. Okay? So if your application is voice, real-time traffic, the latency requirement is like 100 milliseconds or 50 milliseconds. If it's a different application, like data, where you are doing TCP transfer, it could be longer. There's no huge hurry. Or video streaming, where you have a huge buffer in your receiver, again, no huge hurry. You can take a delay given by the size of your buffer. So this delay requirement is a function of the application. Whenever this number is less than that, I call this fast fading. Whenever it's larger than that, I call it slow fading. So that's my rough characterization of fast fading versus slow fading. So you can ask the question, why do I make this definition? Of course, I am standing here on the stage. I can make whatever definition I want. However, it should make some sense, right? So why does it make sense? If you think about it, first of all, is slow fading good or fast fading good? Or let me ask you another question. Is flat fading good or frequency selective fading good? In other words, if you have a choice, you can choose what channel you are communicating over. Would you prefer a flat or frequency selective channel? Frequency selective fading channel, right? Because if it's a flat channel, then if you're in a no, then the whole channel goes down. You have no means of communicating. Frequency selective, it goes up and down, so you're in nodes in one place and peaks in another place. The chance of everything going down is very small. Okay? So you prefer a frequency selective versus a flat fading from a fundamental communication point of view. Of course, there are other considerations, like the complexity of your receiver and so forth, that may, from that point of view, you may prefer, you may have a different preference. But from a fundamental information point of view, i.e. how to get information through, you definitely prefer a frequency selective fading. Similarly, we prefer a fast fading versus slow fading channel. Because a fast fading means what? That means within the latency timescale for which you have to deliver the traffic, you have an opportunity to see the channel going up and down. And therefore, if it goes down at some time, you may be able to see a better channel next time. If it's a slow fading, then within the time latency requirement, the channel is essentially constant. Either it's down or up. If it's down, you're gone. You don't have anything to send. So in terms of reliability, it's not very good. So that's why I prefer a fast versus slow fading. And that's why I define fast and slow fading this way. It's the temporal analog to the frequency domain. Okay, there's a fifth definition called an underspread channel. Okay, and the underspread channel is defined by the relationship between the delay spread and the coherence time. Okay, so all this definition is in terms of the coherence time. This definition is in terms of the coherence bandwidth, which is reciprocal of the coherence delay spread. And this definition is a comparison between the delay spread and the coherence time. Okay? Now, why is it important? First of all, most wise channels we see are underspread channel. Okay? Why? Just order of magnitude. Coherence time depends on the carrier frequency of the order of maybe several tens of milliseconds. Say 100 hertz would be 10 millisecond coherence time. Slower speed, even more. So at least going to be 10 or multiple of tens of millisecond. How about the delay spread? What kind of numbers are we looking at for delay spread? It's important to have numbers in mind. What's the number? What's the order of magnitude for delay spread? Sorry? Microsecond, right? Delay spread is a delay. We have a speed of light here divided by the distance travel, or the other way around. Distance travel divided by speed of light, okay? So typically in an outdoor environment, it will be of the order of microsecond. In an indoor environment, maybe nanosecond, okay? So you can see that the delay spread is several orders of magnitude smaller than the coherence time. So that's why underspread is a common phenomenon for wireless communication system. Now, why is that important from communication point of view? A underspread channel means what? So think about it. We have a linear time varying channel, right? That's a basic model for wireless communication. How come we never teach students in undergraduate, at least I don't teach students, linear time varying channel? Because they're kind of messy. All this stuff about frequency domain, frequency response, etc., they all apply to linear time invariant channel. So linear time varying channel in the full generality is a mess. However, for underspread channel, okay, essentially, one can think of this channel as a time invariant channel over a very long time scale given by the coherence time. And then slowly, it will change to another linear time invariant channel. So the linear time invariant channel is characterized by the delay spread. That's how much memory there is. Okay? The time variation is characterized by the coherence time. But this is taking place at a much longer time scale compared to the delay spread. Delay spread, microseconds, coherence time, millisecond. So therefore, we can also, because of this decomposition, we can use whatever we learned for linear time invariant channel and apply to this linear time variant channel. Okay? We'll see some applications of that as I talked about communication scheme in the next section. Okay, so at this point, it's good to just recap what we learned. We have 4 numbers here. Okay, let's test people. Okay, what are the 4 numbers? Maybe I shouldn't draw it this way. Okay. The 4 numbers are coherence bandwidth, coherence time, Doppler spread, and delay spread. Okay? So, question. Are these four completely independent numbers? No. Which are related to each other? Coherence bandwidth is related to the delay spread, they're reciprocal of each other. The coherence time is related to the Doppler spread. And the Dopplers and the relationship between TC and TD dictates whether the channel is underspread or not. Okay? So that summarizes our discussion so far. So now we move on to statistical model. Okay, so far we've talked about deterministic physical model to give you some sense of the connection of the physical parameters to the channel. But physical model is a mess. The reason is the following. If I look at the physical channel, it is a sum of many multipaths, each with their gains and delays and rotations and phase rotation and so forth. Obviously, I'm not going to design a communication system for a specific impulse response because I don't know what I'm going to see. I'm going to be able to design a communication system which works for most channel response or works on the average. So therefore, we need some sense of the likelihood of seeing the realization of the deterministic channel. So therefore, we need to put some probability distribution on this thing. Now, if you look at this channel and you ask yourself, okay, let's say I put a distribution first on the number of paths I have. Say I may likely get 15 paths, 10 paths, 20 paths. And now you start thinking about, geez, how do I put a distribution on AI? How do I put a distribution on tau I? It's a bit hard. It's a bit hard. But fortunately, in many cases, we don't need to do that. And the reason is because I don't really care about the distribution of this individual AI and tau I. All I care about is the aggregation effect. Okay? So all I care about is the aggregation effect. And the more aggregation there are, the more statistically reliable I can to model them. And in fact, if there are many of them, each path conveys only a small part of the total energy, then a natural model that one could use is a Gaussian model. So because of central limit theorem, we can think of adding a bunch of independent random effects. These paths are coming from different places, so presumably they're more or less independent. And if I add a lot of them together, then you can use a Gaussian model. And this is a so-called Rayleigh model. So the Rayleigh model is a very popular model. It's, of course, a theoretical ideal model, but it's useful to use to think about the problem. And in this case, if I add up all these things together, I can model as Gaussian random variable. And remember, we're dealing with a complex number here. So complex baseband. Okay? All right? Then the real and measuring part are both Gaussian. Okay? And this is called a circular symmetric Gaussian random variable. Complex number, both real and the measuring part are independent Gaussian random variable. Okay, let's think a little bit about this. It's called complex circular symmetric Gaussian. So it's as though complex is not enough. We add a few more words to make it even more complicated. But there's a reason for this. Okay. Now, circular symmetric is a very key feature of a wireless channel model. What does circular symmetric mean? Circular symmetric means that the complex random variable, the phase of that random variable, is uniformly distributed between 0 and 2 pi. Therefore, if you look at that random variable as a complex random variable, there's no preference in terms of direction. Okay? So in other words, if I look at the real and imaginary point, and I plot the PDF of this thing, and I look at it from above, and I plot the contours, it's flat. So it's spherically symmetrical, circularly symmetrical. It's equivalent to saying that the real and imaginary part are independent of each other. Okay? What does this make sense? Why maybe the real and imaginary part are not independent of each other? Because I only assume that it's Gaussian because of central limit theorem. But, you know, the real and imaginary part may not be dependent of each other. Why does it make sense? So you've got to think back at the model here. What does the phase represent? What's the phase a function of? Sorry? The phase is a function of delay. More basic is a function of the location of where you are. Right? So you're sending waves at me, right? The phase is essentially saying that where which part of that wave am I on? So therefore, if I change, remember, a distance of the order of a wavelength, the phases change a huge amount already, from 0 to pi. Right? So therefore, if I randomly plop you down on a point in space, can you tell me whether it's more likely to be 90 degrees, or 120 degrees, or 180 degrees? No, right? Because we're dealing with a very big network here. Many kilometers, maybe, or a few kilometers. I throw you down, and the question is which point you are in terms of the wavelength, 0.3 meter. Who knows? So uniformly between 0 and 2 pi is a very reasonable assumption. In fact, whereas the Gaussian is sometimes questionable, the circular symmetric is beyond questionable. Okay? Unless you are sitting right beside the antennas, but then you have other problems to worry about. Okay? That was a joke. It's okay. Maybe I should borrow these signs, you know. A joke is coming or something. Okay. All right. People also use the Gaussian model. Gaussian model is to say that, well, there may be one significant path, which is a line of sight, plus a lot of scatter path. So the significant path is given by a deterministic part with a random phase, again, always random phase, plus a Gaussian part, which is the aggregation of the scatter path. Okay? So Gaussian, really, people use that. If you work at a place like Qualcomm, then you have to do a lot of simulation. That's part of the game. And then they will have some standard to software where you can simulate channel variation. So we talk about channel variation, but how do you simulate the statistical variation of the channel? One model that people use, just in case you see it, is Clark's model or Jake's model, where you model the scatter as coming from all different directions. And then you can look at that fading process as like a random process. This is the variation over time. This is the autocorrelation function of that fading process. So you can see that as I look at different times, they get more and more or less independent. And there's a notion of the power spectrum of that. Okay. Finally, to complete our model so that we can move on to chapter 3, of course, our reason of existence is because of noise. Without noise, it's not very funny. Because without noise, then you have no problem in decoding the information given the output, given the input. Given input, of course, there's no problem. But given the output, decoding the input is not a problem without noise. So we add noise. And the noise we typically add are, again, both the I phase and the Q phase are hit by independent Gaussian noise. So therefore, you can think of that noise as a complex random variable. Again, complex Gaussian, circular symmetric because it's independent in both the I phase and the Q phase, variance and node. Okay? So that completes our model. Very often we'll focus on the flat fading model. In the flat fading model, remember, it's a single tab. Then I can ignore the indexing by L here and just call it h of m. M dictates, again, the time variation. Okay. So that's our model. We'll use this throughout the course. So we're done. In this section of the course, we have understood how the physical parameters affect the channel, particularly the time and frequency selectivity of the channel. We have also looked at a few statistical models. Okay, so let's move on to, shall we move on? Yeah, we just took a break, right? So not too many breaks. Okay, let's move on to chapter 3. Okay, so chapter 3 deals with diversity, and the main story is the following. Remember, again, always keep your mental picture. I won't show that picture again and again of this channel, which varies 20 dB in dynamic range. Okay, I'm confronting with this channel, and the thing I really worry about is that when the channel is in deep fade, then I cannot get my bits through. So I'm really worried about that. And diversity is really a way for me to get more resolvable signal paths. So remember that fading occurs because I can't resolve my signal paths. If I have a bandwidth limitation, I can't really see these signal paths. Although they're there, I can't see it at the receiver. They all get bunched up together. And so they start canceling each other, and I'm in deep fade, and I can't communicate. So you've got to first physically try to get more resolution into your multipath so that you can get individual resolvable signal paths that fade independent of each other. Okay? Then you can get more reliability. What we're talking about is now, what this is called is diversity. By providing more resolution, you get more diversity. And it turns out that diversity can be provided across different modalities, time, frequency, and space. We'll talk about all of these. And the name of the game turns out to be, once you have the physical diversity, it's not so easy, it's not so difficult to design a communication scheme that exploits, that gets that diversity. However, what is more interesting is how do you get that diversity in an efficient manner? That is, to still keep the data rate to be high. And that's the focus of this lecture, this section. Okay, so to start thinking about this, we should start with a baseline channel. Baseline channel, it's good to have baseline. The baseline channel is our friendly AWGN channel. AW channel, additive white Gaussian noise channel. So this is the simplest channel you can think of, at least from a wireless communication person point of view. Y equals X plus W. You transmit a symbol X, you get hit by Gaussian noise W, you receive Y. Okay? So let's go through the most simple example. You send a BPSK, more jargon, sorry. Binary phase shift keying is so communication engineers, they want to be their own club, right? They don't want to admit people. So they make very complicated terminology for a very simple idea. And the idea is you send plus or minus A, and they call it BPSK. 4 letters for 1 bit of information or less. Plus or minus A. All right, so it's 1 bit of information. The error probability, this is just a quick review of digital communication really, is given by our friendly Q function. Remember now, Q function is the tail of a Gaussian random variable. A divided by n naught over 2, where A is the amplitude and n naught is my noise variance. Formula very complicated. Let's look at the picture. All right. Picture is very simple. You send plus or minus A here. I dictated by UA and UB more generally. You are hit by Gaussian noise. You decide based on whether it's on the left or the right of the threshold. You make an error if this is the transmitted symbol, but the noise kicks you over to the other end. So the error probability is essentially the tail of the Gaussian random Gaussian noise. And so the Q function appears. The Q function is the tail, the probability of the tail of a Gaussian random variable. It's the ratio of the amplitude and the noise. And I define this by a very key parameter is signal-to-noise ratio. Signal-to-noise ratio is defined to be the energy of the signal divided by the noise. Okay, A squared over N naught. All right? So the first thing to observe is that if I increase my SNR, how much impact does that have on the error probability? Okay? And the Q function is well known to have an exponential tail. Okay, so the Q function is exponential in the SNR. Okay? You can see that in the picture. Shoom, this decreases like crazy here. Proof by example. And therefore, if I increase my SNR, the error probability is very fast. So that's a good thing. Why? Because suppose the error probability, you're trying to meet a certain requirement, 10 to the minus 3, minus 4. And this tells you that, you know, if I don't meet my requirement now, I just have to increase my transmit power a little bit. Okay? And then I'll be able to meet it. It's no big deal. All right? So let's use that as the basis of evaluating how a fading channel behaves. So now, I have a flat fading channel. Very simple, Rayleigh flat fading channel. So all I have is y equals hx plus w. The only difference between AWG and 1 is this h. And this h is a Gaussian random variable, circular symmetric, a random fading. Okay? So now, suppose I send again x equals plus or minus a. And now I want to do demodulation. Now, first observation is if h is not known at the receiver, I can't demodulate. Right? Because h has random phase. And obviously, if I send plus or minus a and I don't know what that random phase the channel is doing to my symbol, I cannot demodulate what is plus or minus a sent. Okay? So therefore, to demodulate, you have to, for this particular modulation scheme, you have to estimate the channel. Okay? So in practice, what people do often is they send some kind of training or pilot symbol every now and then. Okay? Since the coherence time is typically pretty long compared to the symbol time, so symbol time may be of the order of microseconds. So if you're running at, say, a megahertz symbol rate, then you're talking about 10 to the power 6. One symbol every 10 to the minus 6 every microsecond. Coherence time is like 10 of milliseconds. So typically you see a few hundred or even 1,000 symbols every coherence time. You have plenty of time to spend some of the resource to estimate the channel first. The receiver knows the channel, then you can do data demodulation. So this is called coherent detection. You can also do non-coherent detection in very fast environment, but that you can look at in the book. All right. So now, once we do coherent demodulation, everything falls into place, because if we do coherent demodulation, the error probability is very similar to the same problem as before, because all I need to do is to divide the whole thing by h. This is no rocket science here. Divide everything by h, and you just apply the same formula as before, except the signal-to-noise ratio is altered by h, because h is now changing the received signal-to-noise ratio. Okay? So in other words, if we condition on a specific realization of h, this is the error probability. Okay? So now if we want to compute some kind of average error probability as an average performance measure, then if I average over this, you can do the math. I don't like to do math on the whiteboard here because the math could come up wrong. That turns out to be this expression. And at highest NR, turns out to be this expression. Okay? All right. So now we plot the performance. So this is our, wireless engineers love to plot things. So we plot a lot of stuff. As a function of the signal-noise ratio in dB scale, I'm plotting my error probability in also log scale. So here is my AWGN channel, the solid curve in the bottom. You can see that if I increase my SNR, the error probability falls like crazy, and that's exponential decrease. You can see that. And this is the so-called waterfall curve. Okay? Water is falling. All right? Now, if I look at the coherent BPSK, that's the dotted line in the middle. And you can see that as I increase the SNR, this is not good. The error probability is decreasing very slowly. Okay? And the reason is very simple. The reason is because the decrease is 1 over SNR, whereas the other one is exponential in SNR. So of course, exponential is much, much faster than 1 over SNR. And so that's a problem. Okay? Now, even if you do non-coherent, it turns out to be not that big a difference. So that's why we focus on coherent only. So now we have a problem here, is that once you're fading, the average error probability performance is much worse than a non-faded channel. Okay? And the reason, you can see, now I don't like to do integration. The last time I did integration was in high school. And I've left high school quite a few years ago, maybe 2 or 3 years ago. So to get this expression, you do integration. Okay? But integration, to me, doesn't offer much insight. So let me look at it, the problem in a different way and explain to you what went wrong. What went wrong? WWW. Okay? If I look at this expression, okay? If I look at this expression, again, I look at this h squared times SNR. This is the instantaneous received SNR when the random channel is at a value h. To get the average error probability, I average over this expression. However, before I average it, let me try to figure out what channel is actually contributing to the bad situation here. So if you think about it, if the channel strength is much larger than 1 over SNR, that means what? That means the received SNR is much larger than 0 dB, much larger than 1. Then the error probability is actually very small. Right? Why? Because of this property of the Q function, right? The Q function has a rapidly decreasing tail, which means that once the argument here becomes much larger than 1, then it's essentially vanished like crazy. So the only place where errors typically occur is when h squared is more than 1 over SNR. That means when the received SNR is less than, say, 0 dB. That's when all the errors occur. So essentially, the situation is pretty simple. You make an error when the channel is less than 1 over SNR, and most of the time otherwise, you don't make any errors. Okay? So errors occur because of both channel and noise. But now we can figure out this typical way of making error. The typical way of making error is when the channel is bad and the noise is just slightly pushed over, rather than the channel being strong and the noise kick you over. Because once the channel is strong, the noise is very, very hard to kick you over because you have Gaussian noise. So the typical error is occurring when this event happens. That is this event. And this probability, unfortunately, is very high. It's only of the order of 1 over SNR. Okay? So why is that? Let's plot something here. So h is a rarely fading random variable. So h is CN01. So you can compute the PDF of h squared. That's just an exercise. This is exponential with mean 1. Okay? So I plot the PDF. Okay? All right? Now, the probability you're in a deep fade is when this channel, H, is less than 1 over SNR, the threshold. So the probability is this area. So you can see that this height for an exponential random variable of mean 1 is 1. So the probability of this is the area of this. And for high SNR, is essentially 1 times the width, which is 1 over SNR. That's why. Now, why am I keep on focusing on high SNR here? High SNR means, 15, 20 dB, this kind of range. Well, for this particular problem, there's no point in focusing on low SNR. Because low SNR means your error probability sucks. Okay? So we'll come back to low SNR later on when we have enough tools. But for this particular example, high SNR is the right thing to focus on. Okay? So high SNR means that your error probability is of the order of 1 over SNR only. So the problem is that if you look at this distribution, the probability you're in a deep fade is very high. It's of the order of 1 over SNR. Unfortunately, this is very small, but we're not worried about that. We're worried about the channel being small. Okay? All right. So typical error is good. So now, what have we accomplished here? Well, you may ask me, geez, I already have an explicit formula for the error probability. I actually do a Taylor series expansion to get this formula. Very exact, very nice. Why am I doing this over again? And instead get a wrong answer? What's the point of doing that? The point of doing that is, although I get a wrong answer, I don't get exactly 1 over 4 SNR. I get the right dependency on SNR. And that's the most important thing, because SNR is something that you could, is a design parameter. So you want to know how your performance depends on the design parameter. So this way of looking at the problem gives me more insight to what's going on than just computing an integral. And once you have that insight, then you can use that to understand more and more complicated scenario. And that's what we're going to do. In more and more complicated scenario, you may not be able to compute these integrals explicitly every time. But you can use this insight to help you to do analysis and design. Okay? So remember, the lesson to learn here is the typical error event is one in which the channel is in deep fade, i.e. here, rather than the noise being large. Okay? All right. Let me take a slight detour. Before I go on to talk about diversity techniques and see how I can improve this, let me talk about one other issue that may bother some of you. Okay? So, I've used BPSK. Okay? From the communication system point of view, what does BPSK mean? BPSK means I'm sending real symbol, right? Plus or minus A. So that means I'm not using the Q phase, right? I'm only using the I phase. So remember, in my communication system, I have 2 inputs, right? Because I'm inputting a complex number. There's real and there's imaginary. So BPSK means I'm only using one of them and I'm not using the other one. That's stupid, right? I should use the other one. And that's why people use QPSK. Okay? So QPSK delivers 2 bits per symbol. BPSK delivers 1 bit. So therefore, seems to be better. But in what sense is this better? In what sense is this better? So one can compare, and one can say, geez, I don't like complex stuff. I don't like imaginary stuff. I like real stuff. So I'm going to keep on using my real I phase only and not use the Q phase, but I still insist on sending 2 bits per symbol. I want to match your rate. And I want to compare how much power I need to consume to match that rate. Okay? So if I want to match your rate, then I have to send 2 bits per real symbol. So I need to use a higher constellation. And here another notation for PAM. PAM stands for Pulse Amplitude Modulation. The names become senseless because they were invented 50 years ago for some other odd historic reasons. For PAM really means, it's a complicated way of saying, I want to send 4 values to send 2 bits. Okay? So in other words, the comparison here is that, okay? So QPSK, the constellation of QPSK is like this. So this is my real and this is imaginary. Okay? This is QPSK. These are my 4 possible values. Okay? 2 bits. PAM, for PAM, the same 2 bits, but I only use the real part to send, means this. Okay? All right? If I want to make sure the error probability is the same in the 2 cases, essentially what I want is to make sure that the distance, the nearest distance between these points, are the same in these 2 cases. Right? If the nearest distance are the same, then I can ask the question, which one uses more power? The PAM uses more power. You can see from the picture, right? Here I have 2 dimensions to put these points on. Here I only have 1 dimension, so as a result, I have to make it longer, further away, more power. So QPSK is more efficient. In fact, the calculation says that I need 4 dB more transmit power. Okay? 4 dB essentially means a few $1 billion here. Okay? In a company like Qualcomm, if you save half a dB, you're already a hero for the month. So 4 dB is a lot to waste. And the point of this is I want to introduce a concept which will recur throughout the whole course, which is the notion of degrees of freedom. So QPSK is more efficient because I'm packing points in a higher dimensional space, whereas for PAM is less efficient because I'm packing the same number of points in a confined low dimensional space. Actually, this picture is very generic to communication. In fact, the idea of coding is really the idea of efficient use of the high dimensional space. Okay? So this is a simple example of that. And this point will recur throughout again. So let us ponder here and make sure people sort of understand this point. Okay? All right? Okay. So 4 dB more. Degrees of freedom, I'm using more. Okay. All right. Okay. So now we take a slight detour. We took a slight detour in talking about degrees of freedom. But now let's go back to our main thrust of the section here, which is to talk about diversity. Okay? So what's the problem here? The problem is the gap between this curve and this curve. So I am now here with my flat fading channel. I want to be here. How do I get from here to here? Okay? To get from here to here, from here to there, I need diversity. I need more diversity in the system. The reason is because if I'm in a deep fade, then I'm screwed up. So the typical error event is when I'm deep fade. I need to make sure the probability of that kind of event is smaller in some sense. So how do I do that? Well, there are several different ways of introducing diversity. The simplest is time diversity. Okay? So here's the picture. Now, imagine I'm in a fast fading channel. All right, quick quiz. Fast fading means what? Whatever. Fast fading means what? Coherence time is? Coherence time is greater than delay requirement. That's the opposite. Coherence time is less than the delay requirement. So in the context of a communication system, what does that mean? That means if I look over different times, okay, if I look over different times, the channel varies. This is a cartoon picture, of course, such that over the time scale of interest, the channel goes up and down. Now, if the delay requirement is longer than the coherence time, that means what? That means I am not forced. So if the information symbol comes in at this time, that means I'm not forced to spit out the information at the receiver at this coherence time. Because my delay requirement is longer than the coherence time, I can wait for the next coherent time or the next coherence time before I spit out the information, the decoding, at the receiver. That means now I can afford to code over a time scale which is longer than a coherence time. That means within the coding time scale, I will see variation in the channel. And that variation gives me diversity. Because now the probability, so now, even if this guy is in a deep fade, the other guys can potentially help me out. So that's the idea. So let's think about how we can implement that idea. So think about this example. I do coding like this. I have one code word. I send this code word over the air. The receiver decodes. I send another code word, another code word, another code word. So this is coding. Does it give me diversity? No. Because these code words, they all sit within one coherence time. So I do a lot of coding, turbo code, LDPC, all these things that Berkeley is going to tell you about when he visits. By the way, how come Berkeley seems to be having a good time all the time? Such relaxing pictures. Whereas I'm just like staring at you. You know, it's not very fair.
I think that's why your book is out.
Okay. So you code, but then when the channel is in a fade, you lose the entire code word. So a natural way to do it is not only you need to do coding, but you need to interleave. You need to interleave. So interleaving is an important idea. So what does that mean? It means the following. I take this code word, 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 and instead of sending it all in one shot, one after the other, I interleave them. So I send the first symbol of the first code word first, and then the first symbol of the second code word, and then the first symbol of the third code word, and then after a while I come back to the first code word. That way, if you look at this particular code word, his symbols are dispersed over time, okay, at different times. So if this channel is in deep fade over this coherence time, then you lose a bunch of symbols, but you only lose one symbol from each code word. And therefore, you can now use the coding gain to decode that symbol, decode the information, even though you have lost one of the symbols. Before, I lost all my symbols, so there's no way of it to decode. Even a Berkeley, relaxing, still can't do anything about that. All right? All right. Okay, so coding and interleaving. So just to give you some sense of how this is done in practice, in a GSM system, I'm sure most of you, a lot of you, even in San Diego, uses GSM phones. Typically, coding and interleaving is happening over 8 time slots. So in GSM, different users assign different time slots. The coding is done over 8 time slots here, and interleaving. So you basically take one symbol, one coded symbol, coded code word, you split up into 8 time slots. So now you can see the amount of time diversity I can get from this channel. Okay? Now the amount of time diversity is limited by the delay constraint. How do we see that? Well, if I have no delay constraint, or if I have very lax delay constraint, then I can interleave over many, many time slots. Yeah? Many, many time slots. There's no limit. However, the delay constraint means what? I need to decode after a certain time. I can't wait forever. I got to decode after a certain time. And that limits the number of time slots they chose. GSM is mainly a voice system, of course. the number of time slots is chosen to match the voice delay requirement, and that's roughly about 50 to 100 milliseconds. Okay. It is also limited by how fast the channel varies. Okay? So, or 40 milliseconds. Okay? So, if you want to get the full diversity, the maximum diversity you can get here is 8 when the channel coherence time is such that the fading is independent from time slot to time slot. To get that, you need a pretty fast speed, 30 kilometers per hour. If you calculate based on the rule of thumb that we have in terms of coherence time, you get a condition on the speed. Okay? So actually, this is one of the problems of time diversity. So time diversity is one type of diversity, but very rarely do one build a system completely reliant on just having time diversity. And the reason is because of this. You need to be moving, or the environment needs to be changing to get time diversity. Okay? So, and there's no way to guarantee that the user always moves. If it's move, it's a good thing, and you get diversity, you get more reliable communication, it's a good thing. But you know, you cannot like have cell phones that keep on triggering the people to move around. That's probably not very practical. So time diversity is only one mode diversity. Okay. All right. So how do we do coding? So here we say that we do coding and interleaving. So let me give you 2 examples of how we do coding. Number 1 example is a very simple example. Okay, is repetition code. So there's always a very simple code. Okay, and this code, even high school students can do. Repetition. You repeat the same symbol over and over again. Okay? So, all right. So what's the channel model here? I have a code word. Okay? I have a code word. Okay? Code word is a vector x. There are L symbols. Okay, so this constitutes my code word. I send this at different coherence time because I've already interleaved. Okay? So now x1 will see channel h1. Okay, this is a flat fading channel. Remember, this is my Rayleigh flat fading channel. And I receive something. X2 will see H2. And if these symbols are sent at different coherence time, H1, H2 can be assumed to be independent. Up till HL. Okay? All right? So that's the picture. So those are the equations for this picture. All right? YL equals HL XL plus WL. All right? Okay. Now, what is repetition coding? So coding is nothing but a way of mapping information symbols to these code words, to this code word, these components. Repetition coding is one in which you just keep on repeating the same symbol over and over again. So that is when all these guys are the same. Okay? So I set them to be X for all L. And so if I write in vector notation, okay, so if I set all this to be equal to X, etc., then in vector notation, my received vector Y is equal to the vector H times X plus noise. Okay? So that's what I wrote down there. So now we have to preparing ourselves for MIMO. We have to start using vector notation here. Y equals HX plus W. All right? the received vector y, L components, is equal to the channel vector h times the transmitted symbol x plus the noise w. Okay? How do I do detection? This problem is the classic vector detection problem in white Gaussian noise. And here's the picture. Okay? Now, in general, what I'm doing here, I am transmitting information in terms of vectors. So here, whoa, I'm showing too much. I'm sending two vectors, UA and UB. Okay? And I want to be able to detect whether UA or UB is transmitted. This is the same problem as the BPSK problem, except now I'm sending vectors instead of sending scalars. Okay? 2 points. I need to figure out which one of the 2 points were transmitted. The optimal detection rule is, of course, to choose the receive vector to be closest. Choose the one which is closest to the receive vector, in this case, UB. So in terms of this picture, what I'm doing is I'm drawing the hyperplane, which is perpendicular to UA, UB. And the blue, I decide UB. The white, I decide UA. That's it. Okay? What does that mean geometrically? Another way of thinking about that is the following. Is that I'm taking this y here. I am projecting it onto the line connecting UA and UB. I call that projection y tilde. If y tilde is positive, I decide UB. If y tilde is negative, I decide UA. That's it. Okay? So now, you can see that this problem is actually exactly the same problem as the scalar case. Because the scalar case is nothing but obtaining by tilting your head about 30 degrees, thinking about this dotted line as your x-axis, and do decision on this axis. So in other words, although you are living in a high-dimensional space, your decision is only happening at the scalar level. Okay? If you apply this to our problem, what is UA and UB? Suppose I send x to be plus or minus a here. Okay? Then that means what? That means you either send the vector h times a or the vector h times minus a. Those are your two options. Okay? So therefore, I set UA to be plus AH, UB to be minus AH. Those are my two vectors. I want to distinguish one bit of information. I receive a vector, and this is the picture. So this means that if I project y onto h, so this vector, in this example, is precisely the vector aligned with h. So if I project the received vector onto h, then this is sufficient for me to decide information. So this is called a sufficient statistic, match filtering. So this is what people call match filtering. I want to match my receiver to the channel. In this case, the channel is the vector h1 up to hl. Okay? Are people comfortable with this kind of calculation? Because I'm going to do it over and over again. Any question now? Okay. All right. Forever silent then. Okay. All right. So now, let's go back to our diversity problem. If I do this projection, what is the end game? The end game is I set y equals hx plus w into this formula, and now I get y tilde to be equal to norm of h times x plus w. So the scalar detection problem that is reduced from the vectors detection problem is the same as the scalar detection problem, except that the channel has changed from the scalar h to the norm of the whole vector h. Okay? So that's it. If you do the calculation, that's what you're going to get. So now, when are we going to be in deep fade? So now we have a channel derived from our coded and interleaved system, repetition coded, simple. Okay? When are we going to be in deep fade? When are we going to be in trouble? Sorry? When the norm of h is less than 1 over SNR. When the norm of h squared is less than 1 over SNR. That will be the deep fade event. Okay? All right? So remember, in the scalar case, in the, I guess let's call it no diversity case, this is a deep fade event. So now with time diversity, it becomes this event. So now h is a whole vector. Okay? Obviously, we're in a better shape here. How much better? Let's compute. Okay? So here, I'm plotting the PDF of this random variable, norm of h squared, as a function for different L, where L is the number of diversity branches, so to speak, number of symbols. So when L equals to 1, anyone remembers what this distribution is? Exponential. When L equals to 2, a different distribution. It turns out that there's a name for this distribution. It's called a chi-square with 2L degrees of freedom. Doesn't matter what the name is, but this is what the plots are. What is the important feature of these PDF that we should focus on when we want to understand the deep fade event? Deep fade event means what? Means that we're here, close to 0. And you see that we have improvement. When L equals to 1, this probability is large. When L equals to 2, the probability is smaller. When L equals to 3, the probability is even smaller, and so forth. Okay, in fact, one can estimate this probability is proportional to 1 over alpha L factorial, epsilon to the power L, where epsilon is a small number. So you can think of epsilon is precisely equal to 1 over SNR in this problem. So this error probability is like 1 over L factorial, okay, times 1 to the SNR to the power L. So we plot the error probability curves. We see the improvement, okay? When L equals to 1, we have this curve. As we improve L, this curve shifts down. The AWGN curve is somewhere here, waterfall curve. And now we are closing the gap between the no diversity situation and AWGN situation with time diversity. Okay? Now, let's understand this. Why do we get the 1 over SNR L to the power L here? The 1 over L factorial is a bit hard to explain, but the importance is the dependency on SNR. So we can figure that out, right? When do you get a deep fade? You get a deep fade when the norm of h is small. Yeah? When is the norm of h small? When all components are small. The components are independent. Okay? That means you get a power of L here because the independent event. So that's the L. Okay? When you have no diversity, if one component dies, then you die. When you have diversity, you die only when all L components die. And those are independent events. Each occur roughly with probability 1 over SNR. So therefore, the probability is 1 over SNR to the power L. If I look at this curve, the slope of this curve is precisely negative. Is the power is this power. Okay? So as I increase L, the slope of this curve increases. Can anyone tell me, if I plot the AWGN curve, what's the asymptotic slope of that curve? Sorry? Infinity. So the slope of that curve is negative infinity, actually, negative infinity. Whereas all these things have finite slope, but as you increase L, the finite slope is bigger and bigger, or negative, more and more negative, which is good. Okay. We have a problem here, though. We have excellent error probability performance. We have excellent error probability performance, but we lost out in a lot of stuff. What did we lose out? What are we doing here? What is repetition coding doing for us? Sorry? Yes, but higher level, repetition coding is sending one bit, right? Or one symbol, one information symbol. Every L symbol L channel uses. So as you increase L, the data rate goes down. So the reliability is obtained at the expense of lowering the data rate when we use repetition coding. And then you can start asking a question, is that a fundamental trade-off? In other words, to get more reliability, do I really have to lower the data rate so drastically? And then you think back at our father, since we're dealing with ITA here, Shannon. He told us that no. In fact, that was one of his biggest discoveries, is that if you want reliable communication, it's not necessary to lower your data rate. In fact, you can get reliable communication at a fixed data rate. That's what he told us. We can apply his principle here in this problem. The trick is we have to do more clever coding, repetition coding, though. So we have to graduate from high school to college. And now we're doing more sophisticated coding. OK. All right. So we're sending one symbol every L symbol time. OK. I'm saying the data rate is low. Another way of saying it is, as was remarked earlier, I'm only using 1 degree of freedom. And I'm not really using fully the degrees of freedom in the channel. So the analogy is exactly with the PAM versus QAM example. You want to use all the dimensions of space and not just one of them. Okay? So how to do better? So this leads to the second example that I want to talk about, where, of course, there's been a lot of work done in this kind of coding stuff, but I want to just use 2 examples to illustrate the main feature, the main point. OK. So let's look at this example. This example is called rotation codes. Rotation codes. Let's see what's going on here. OK. So now, I have 2 symbols. OK. BPSK symbols. OK? X1, X2. I want to send these 2 symbols, 2 information symbols, actually, over 2 time instances. I'm assuming you have done interleaving so that these guys will see independent channel. OK? Now, in the case of repetition coding, what we're doing is we're sending X1 and X2 to be the same symbol. And therefore, we can only convey 1 bit of information over 2 time slots. So our data rate is slowed down by half into half bits per symbol. Now, what we want to do is we want to send 2 independent symbols to get back the 2 bits. OK? However, If I send two independent symbols like this, then obviously they will go through independent fading, and therefore if this guy fades, I lose this bit. So I don't have protection. So now I want to be greedy, and I want to have the best of both worlds. I want to be able to send the two bits, but at the same time I want protection, double protection for both bits. How do I do that? And rotation code is one way of doing that. Okay? So how does it work? Instead of sending, so let's look at this picture. So I'm a pretty geometric guy. And if you look at this picture, okay? If I don't do any coding, then what I'm doing is I'm sending 4 points here, okay? All right? By the way, just to clarify, here I'm sending two BPSK symbols over two coherence time here. So these are not I and Q phase, just to minimize the confusion. This is just two BPSK symbol over two different coherence time. Okay? So I have these 4 points here, and these are my 4 possible values that x1, x2 can take on. Each one is plus or minus a. Now, fading, how does fading kill me? Fading will kill me. So the symbol x1 is distinguished by having either a or minus a. So x1 is distinguished horizontally. Okay? So fading in the first dimension refers to the situation where at the receiver, the horizontal dimension gets shrunk. Right? Because H is in deep fade. That means when you receive the signal, it gets squeezed horizontally. And therefore, you can't tell whether it's a minus A or plus A send. You're confused. Noise screw you over. Okay? When the vertical direction is squeezed, then you potentially can lose the second symbol. So that's why if I put it in this way, then I don't have diversity. One of the channel phase, I'm in trouble already. So the clever idea is to rotate this whole constellation by a certain angle such that you can confuse between two adjacent symbols only when both channel fades. That's the idea. Okay? So I'm still using the full dimensional space here because I'm sending 2 bits. But at the same time, I now have double protection for each of those bits. Okay? So how does this work? Okay. Let me just focus on understanding how I could make an error between XA and XB. Okay? So this is, I'm just drawing XA and XB now. All right? Okay? Now, how do I confuse between XA and XB? To get confused between XA and XB, the vertical direction has to be shrunk. Right? The horizontal direction has to be shrunk as well. For example, if I just shrunk the vertical direction, that means the first subchannel fades, then I can use the horizontal separation to tell them apart, and vice versa. So now I have diversity because I have protection against 2 directions. If XA and XB were horizontal with respect to each other, then once the horizontal direction got shrunk, I'm confused already. Okay? So that's it. That's the idea. All right? So, you can do the math, and it turns out that the error probability, so this is again the same vector detection problem. I'm sending 2 vector, and I'm asking myself, what is the error probability conditional on a particular realization of H1, H2? Okay? All right? And it turns out to be given by this formula. And remember, it's always a Q function of the distance between these 2 points, okay, at the receiver. See, all that matters is what happens at the receiver, right? At the transmitter, you can keep a very good distance, but the receiver, the channel will fade on you, may fade on you. So the distance between XA and XB vertically is D2, okay? And after the fading, the channel will multiply by H2. And the horizontal distance is D1 multiplied by the channel effect H1. Okay? So the Euclidean distance between these 2 points at the receiver is precisely D1 squared H1 squared plus D2 squared H2 squared. And that's what enters into the formula there. Okay? So now we're going to figure out explicitly why we have a diversity of 2 and 2 question, which is how much should I rotate this thing by? That's a natural question, right? You need to rotate it by a certain angle. Question, should I rotate it by 90 degrees? Is rotating by 90 degrees a good idea? Why not? Seems round number. If I rotate by 90 degrees, XA will be vertically on top of XC. And I can get them confused. Basically, I want to rotate it such that none of the separation between these 4 points are vertically aligned or horizontally aligned. So let's figure out how to do that. Okay? So I'm looking at this expression to be able to choose the right D1, D2, essentially. I need to figure out what this error probability is in terms of D1, D2. Okay, and this is the expression. So now I'm going to average over the channel. And if I could compute this integral, then I get explicit expression in terms of D1 and D2. And I can optimize it with that. But I remember, right, I told you, I'm very bad at computing integrals. So I don't know how to compute this integral. It's really messy. It's more complicated than the one earlier. But we can use our typical error event thinking to get a heuristic expression of what this is. Okay, what is the deep fade event now? See, every little thing I tell you is pretty simple. But as I build on top of that, it gets a bit more complicated, a bit more complicated, a bit more complicated. So deep fade event is the event in which the received SNR is less than 0 dB, essentially. That means is inside the Q function, this thing is less than 1, of the order of 1. That means that this thing should be less than 1 over SNR. That means roughly this thing and this thing both are less than 1 over SNR. Same order of magnitude. Deep fade when both components are dying on you, right? Both the vertical and the horizontal is squished. Okay? And so approximately, the error event is the event that this is less than 1 over SNR and this is less than 1 over SNR. H1 and H2 are assumed to be independent fading because you have done interleaving already. So therefore, the probability is the product between these two probability. And each one of these probability is approximately 1 over D1 squared times 1 over SNR. You multiply the two numbers, you get this. Okay? 1 over D1 squared times 1 over D2 squared times SNR minus 2. Assuming D1 and D2 are non-zero, of course. Okay? So if D1 and D2 are non-zero, First observation, I get full diversity. I get diversity 2, as I promised. Second, I now can get a handle on how the error probability is related to the distances between the code words, because that's what I'm going to choose. By choosing different rotation angle, I will change the D1, D2. Okay? And it depends on the product distance. So that's funny, because in designing codes for AWGN channel, if people have taken a first digital communication course, then it emphasized that the important thing about code words is the Euclidean distance between code words. In a fading channel, what this says is that the important thing is the product distance between the code words. Okay? So how should I choose my angle? I should choose my angle to optimize the product distance, to make it small as possible. Of course, I want to make sure that the product distance between all pairs of code words is small. So I want to maximize the worst case product distance. And that turns out to be, the optimal angle turns out to be this. This is not very important, but the product distance is an important concept that I want to bring through this example. Okay? All right. Let me just add 1 or 2 slides and we'll go for lunch. Okay? So let's take a high-level view of the situation and try to understand why our code is doing better than repetition code. This point has been mentioned earlier by someone already in the audience, but it's worthwhile going back to this theme again. So in rotation code, I am putting my data points on a 2-dimensional space. 2-dimensional refers to now 2 time instances rather than I and Q phase, but it's still 2-dimensional, and I'm putting these points 2-dimensional. Our repetition code is essentially repeating every symbol over and over again. So in an L equals to 2 repetition code, you always have the first component and second component the same. So therefore, all your constellation points lie on a straight line. Again, if I want to match the data rate in the 2 cases, then I need to have 4 points here to match the 4 points here. Again, you require more power to send these 4 points. And therefore, another way of saying the repetition coding is inefficient is that to send the same data rate and the same error probability, you require much more power. Okay? All right. So we're done with time diversity. After lunch, I'll talk about antenna diversity.